Hello, hello. Can you guys hear me? Uh, okay, we'll be starting in about 5 minutes while everyone else is coming. So hopefully we have a bit of attendance. Otherwise, if you guys missed the live session, then it will be recorded as well. So you can just play it back anytime. And if you have any questions throughout the stream, feel free to pop it in the chat as well. And I will frequently try to answer some of your questions as well. Cool. So we'll start at about 4:05 while everyone else is settling in. Hello. We seem to have more people joining in now, so Welcome to the MATH2089 stream. Today we'll be covering statistics, and tomorrow's session will be covered by Wendy, where we will go over numerical methods. So first of all, can you guys hear me? Is my audio okay? And if you guys have any questions, just feel free to pop it in the chat. I will be frequently looking over the chat, so I'll try to answer your questions there. Alright, in either case, we'll get started. So today we'll be covering the main 5 topics within statistics. It's a little loud. Okay, I will, yes. Okay, let me, I just made myself a little quieter, so let me know if the audio is okay. So, as I said, we'll be covering the 5 main topics within statistics. So we'll be going over sort of the first hour or so, we'll be going over probability theory. And then we'll cover a little bit about random sampling and the central limit theorem, although there aren't any questions on the central limit theorem. And then we'll go over confidence intervals, hypothesis testing, and we'll finish off with ANOVA, or analysis of variance. Cool. All right, let's get started. So probability theory basically just covers the bulk of the first half of the course. So a lot of the time you'll be doing things like expectation and variance. And so today's workshop, I'll try to cover some of the basic concepts, and also I will go over some past paper questions as well. So in this question, we are given that x follows a Bernoulli distribution. So we're given that the probability mass function is given by either 1 minus pi if x is equal to 0, or pi if x is equal to 1. So you immediately know that x is what we call a discrete random variable, because it only covers discrete cases rather than a continuum of values. So the first question asks us to show that the expectation of x equals to pi, and then we want to show that the variance of x equals to pi times 1 minus pi. So these are fairly standard questions. You should be able to do them fairly quickly as well. So remember that the expectation of x is given by the sum of your event x times the probability of your event. So remember that x only covers 2 different cases here, 0 and 1. So our values for x is only 0 or 1, and p of x is either going to be 1 minus pi or pi, depending on what x is. Okay, so here we can see that it's going to be 0 times 1 minus pi, because 1 minus pi is the probability of 0, and 1 times pi, because pi is the probability when x is equal to 1. And that's equal to 0 plus pi, which is pi as what we wanted. The second part, we wanted to show that the variance of x is pi times 1 minus pi. So in order to do that, we kind of want to invoke an equivalent statement for the variance. So the variance of x can be written as the expectation of x squared minus the square of the expectation. And the expectation of x squared here, we just replace the x with x squared. So here we have that the expectation of x squared is given by the sum over all of the x's of x squared times the probability of x. And we don't convert x into x squared here, we just keep it as x. And we just subtract the square of the expectation, but the expectation is just pi, so we subtract pi squared. If we expand the sum out, we get 0 squared times 1 minus pi plus 1 squared times pi. But this is just the same as pi, so we get pi minus pi squared. And if you factorize the pi out, then you get the result that you wanted. Cool. Does anyone have any questions regarding that? So these are fairly straightforward. It shouldn't take you too long to do as well. Okay. The second question is asking us this time for a probability density function because x is going to be a continuous random variable. So in the previous case, we had discrete random variable because your probability mass function only covered discrete cases. Here we have a range of values where x is greater than or equal to 0. So x could be any value from 0 up until infinity. And when x is less than 0, you take all of the negative cases. So you can take irrational numbers, you can take fractions, etc. So we have a continuum of values that you can take. And we want to show that the expectation of x squared equals to 2 mu squared. And then we want to show that it is generally not true that the expectation of g of x equals to g of expectation of x. In other words, you can't just swap g and the expectation, where g is just a function. And we're also given that the expectation of x equals to mu, and hopefully that's not too hard to prove as well. You just integrate from 0 to infinity of this guy times x, and then you should be able to get mu. So the first part, we want to use integration to show that the expectation of x squared equals to 2 mu squared. So how do we do this? Well, first of all, we know that x is should be a continuous random variable. So what that means is that when you take the expectation of x squared, you want to take an integral instead of a sum. Now, the integral is formally defined from minus infinity to infinity, but obviously there will be some simplification that happens. So generally, you don't really have to write this first line, but for formality's sake, we'll write it anyways. And notice that we just replace x with x squared because we're taking the expectation of x squared. Is there a particular reason it's g and not f? No, there is no reason why we didn't have f or g. I think the question just stated g, so we just use g. I guess f is already defined. F is already a predefined function, but what we're actually saying is that for any particular function. So g is just some arbitrary function, not necessarily a predefined function or probability density function. So we try to not use f because f is already defined, and we want to show a more general result that this is not true, but I think it'll also work if we had f instead. Cool. So going back to our integral, we can split this integral up into two separate integrals here. So we have an integral from minus infinity to 0, and then an integral from 0 to infinity. And we can do that because we're just breaking up a bigger area into two separate areas. And notice that in this case, our f of x is going to be 0 because our bounds go from minus infinity to 0, meaning that we are basically taking a sum of all of the negative values, and for all of the negative values, f of x is 0. And when you take the integral of 0, well, you don't get any area. So this first integral tends to 0, and so all we're left with is this integral here. And if we write f of x as what we had before, then we have that it's 1 divided by mu, so we just take the mu out, 1 over mu outside of the integral, and we take the integral from 0 to infinity of x squared times e to the minus x divided by mu. And you can see that we have a product of functions, So the most natural integral technique is integration by parts. So we're going to integrate by parts. We will differentiate x squared because when we differentiate x squared, we get something a lot simpler. And we will also invoke another result later on. And then we want to integrate e to the minus x divided by mu. Because when we differentiate x squared, we need to integrate the other part as well. So if we differentiate x squared, we get 2x. And if we integrate e to the minus x divided by mu, we get minus mu times e to the minus x divided by mu. And you can verify this by just differentiating this function here, and you should be able to get v prime. So using our integration by parts formula, we want to take the integral. The integral becomes uv evaluated from 0 to infinity minus the integral of the product of these two, so v times u prime. And you simplify, so this guy here was simplified to 0, because if you substitute infinity, then e to the minus x divided by mu, that would tend to 0 a lot faster than x squared would tend to infinity. So when you substitute infinity, you get 0, and obviously when you substitute 0, you get 0 as well. So this part here becomes 0, and this part here looks awfully familiar to you. And notice that this looks very similar to e of x. The only difference is that if we had, or the expectation of x had the 1 divided by mu at the front. But it's fine, because what we can do is we can just multiply by 1 over mu, and then we can just we can multiply by mu, and we can divide by mu. And notice that this is your f of x. And so what we get here is the integral from 0 to infinity of x times f of x. And notice that that becomes the expectation of x. But we proved, or well, they showed that the expectation of x is just mu. And so we can just substitute e of x with mu, and we get that it's equal to 2 times mu squared. And so we've proven what we wanted to show. We wanted to show that e of x squared is just 2 mu squared. Does anyone have any questions? Or does it make sense? And we want to show that in general, e of any particular function is not the same as the function of e of x. Can the MATLAB int command do integration by parts as well? I think it can, because integration by parts is a very natural technique to use. So I think MATLAB should be able to integrate any particular function using by parts. Cool. Very good questions. So for part 2, let's go back to our question, kind of remind ourselves. We wanted to show that in general, it is not true that when you take the expectation of g of x, it's equal to g of e of x. And we're going to show that using a particular example. Here we're going to take x squared as our function because we've already found e of x squared. And if we take g of x, then g of capital X is just x squared. And we've already shown that e of g of x, well, that's equal to e of x squared, which is 2 mu squared. But when we swap the order of e and g, then we get that we're taking the square of e of x, but e of x is just mu. So we're taking the square of mu, which is mu squared, but that's not equal to 2 mu squared. And so what we have is that e of g of x is not the same as g of E of x. Cool. So it is not true in general that E of g of x equals to g of E of x. All right. Does anyone have any questions regarding that particular problem? So that problem really just required you to know how to integrate, and once you're able to integrate it, then everything just falls out very nicely. All right, so this next one is still a random variable type question, but this time we are explicitly given the distribution of x and y, and we are asked to calculate different types of probabilities. So let x and y be independent, so I'm just going to highlight this because this is going to be very important later on. But for now, let's just keep in mind that they are independent random variables. And we know that the distribution of x is a Poisson distribution with parameter 2. And y is an exponential distribution with parameter 1. You don't need to memorize what these distributions look like because you either will be provided with you'll be provided with the distributions, or you can search it up if you're allowed. But just know how to use these types of distributions, and I think that's the most important thing with this problem. So we're asked to calculate the probability of x equals to 1, probability of y is less than 1, and then the probability that x is equal to 1 or y is less than 1. So the first one, we're asked to calculate the probability of x equals to 1. So we know that the Poisson distribution is discrete, and it has a probability mass function of, well, if we substitute lambda equals to 2, then we have 2 to the x times e to the minus 2 divided by x factorial, where x is the x equals to x, basically. All right, so we want to just calculate when x equals to 1. So we just substitute x equals to 1, and we have that it's equal to 2 times 1 times 2 to the power of 1 times e to the power of minus 2 divided by 1 factorial, which is 2e to the minus 2. The second part, we have an exponential distribution, but an exponential distribution is continuous with this probability density function. So it's e to the minus x, where x is greater than or equal to 0, and 0 when x is less than 0. So we know that the exponential distribution is continuous, and we want to calculate all of the points where y is less than 1. So we basically calculate all of the possible values where we range from 0 to 1. And remember that because it's a continuous random variable, the sum is not enough because a sum assumes that your distribution is discrete. But because we have an interval from 0 to 1, then we basically need to consider the integral, which is basically smaller and smaller sums. You can basically think of the integral as just a sum over infinitely many values. And so we want to integrate from 0 to 1 the density function, which we're given to be e to the minus x. So we basically calculate this. We just swap the x and y, but you can use x if you wanted to. It doesn't really matter. They're what we call dummy variables. So interchanging x and y doesn't really change the integral itself. And when you integrate this, you should get 1 minus e to the minus 1. So that's just some simple integration. So as long as you know how to integrate it, you'll be fine. The last question is the one that we want to kind of discuss, because this is the harder part. We want to calculate x equals to 1 or y is less than 1. We're given that it's independent, but we're not given that it's mutually exclusive. So we can't just take the probability of x equals to 1 plus the probability of y is less than 1. That in general is not true. We need to consider also the intersection between x equals to 1 and y is less than 1. So let's do that. So we know that the probability that x equals to 1 or y is less than 1 equals to the sum of x equals to 1 and y is less than 1. But then we need to subtract off the intersection between x equals to 1 and y is less than 1. But we know that they are independent. So we use the fact that they are independent to then break up this and part. So we can break this entire thing here into a product of x equals to 1 and y is less than 1. And the reason why we can do this is purely because they're independent. So x equals to 1 doesn't depend on y, and y less than 1 doesn't depend on what x is. And so they are two separate distributions, and so when you take the intersection, that's the same as taking the probability of x equals to 1 and y is less than 1. Cool. So once you do that, you know separately the probability that of x equals to 1 and the probability of y is less than 1. And so you just substitute everything in, and you should simplify this to 1 minus e to the minus 1 plus 2 times e to the minus 3, which is approximately 0.732. So to recap, in order to do these OR problems, you need to break it up into 3 separate components. So you need to break it up into just this component here. So I'll highlight this as yellow. And then you need to break it up into this component here. I'll highlight this in green. And then you need to also consider the intersection as well. Highlight this in light blue. Right, but we know that the intersection, because of the fact that they're independent, that's equal to this. Oops, I will just highlight this. And then you just basically plug everything in because you already know the distribution of x equals to 1 and y is less than 1, and you'll end up with this. Oh, does anyone have any questions regarding this? Oh, okay. Here's another probability theory question. So this time we are given that x and y are independent standard normal variables. So in other words, x and y are normal 0, 1 with mean 0 and standard deviation 1. And we want to calculate the distribution of x plus y, and finally the probability that x plus y is less than 1. So some things about normal variables: when you take the sum of 2 normal variables, you get another normal variable. So we're going to use that fact and also a more general fact to then find the distribution of x plus y. So as we noted before, the distribution of a sum of normal variables is just another normal variable. So x plus y is going to be normally distributed. And more generally, if a is normal with mean mu a and standard deviation sigma squared a, or variance sigma squared a, and b is the same thing but in this time with subscript b, then the sum is going to just be the sum of the means and the sum of the variances. And so if we basically just substitute everything in, then x plus y will be normal 0, 2, because you take the sum of the means to be the new mean, and you take the sum of the variances to be the new variance. And so we have a normal 0 to random variable. Cool. And part 2, remember it asks us to calculate the probability that the sum is less than 1. So remember that x plus y is just another normal variable. So for convenience sake, let's just call it w. And this is just the same thing as finding the probability that w is less than 1 and w is normal 0, 2. So to find this, the most natural thing is to just standardize it so that we have something in terms of the standard normal distribution instead, because the standard normal is a lot nicer to deal with. So if we standardize it, we get w minus mu divided by sigma. That's the normal, that's the standard normal conversion. And we know that z is going to be normal 0, 1. So this is just equivalent of finding z is less than w minus 0 divided by the square root of 2. Remember that sigma is the square root of the variance, and the variance was 2. So the standard deviation is just the square root of 2. Is it possible that these slides will be posted, I think, a few days after the workshops. So you'll have all of the information here. So they will be posted on the MathSoc website. We will post an announcement when they are all posted up. So be on the lookout for that. Anyway, back to this. So remember that we wanted to find w is less than 1. So this is the same thing as finding the probability that z is less than 1 divided by the square root of 2. And you can just chuck that into MATLAB using norminv or using some other function, inbuilt function in MATLAB, and you'll get something like 0.77935. And for it to make sense, you think, okay, well, it's a probability, so it should be a number between 0 and 1, and clearly it is, so it makes sense. Cool. Does anyone have any questions? All right, perfect. Let's move on then. So this one comes from another statistics course, just because I couldn't really find anything regarding independence and mutual exclusion. So this one comes from the MATH2089 paper, 2018 semester 1. And we are given that A and B are two events in some sample space. And we're given that the probability of A is greater than 0, and the probability of B is also greater than 0. So what's the difference between norm CDF and norminv? So norm CDF basically calculates the cumulative distribution function. So I guess I'll find a place to kind of write it. Okay, I'll draw it up here. So remember that the norm so if I take norm, oh my gosh, my writing is going to be atrocious, but let's just ignore my handwriting because I can't draw with a trackpad. But norm CDF is what we call the cumulative distribution function. So basically you can think of it as just you're accumulating different types of parts here. Norminv, on the other hand, is what we call the inverse. So norminv, so here norm CDF basically takes, I guess, the integral from 0 to x, of f of x. So f of x here is basically, it's f of y. So f of y in this case is the distribution function of the normal distribution. Norm inv, on the other hand, so norm inv is basically what we want to calculate when we want to calculate, say, probabilities. We basically want to calculate, say, the probability that x is less than a, and that's equal to some value, let's just say, I don't know, 0.5 or something. And what it would do is it will calculate the value of a here. So you can think of it as the inverse of the normal distribution. So it will find whatever is inside here that matches 0.5. And you have to give it the particular distribution as well. So norm CDF basically calculates the cumulative distribution function. Norm inv calculates, well, whatever value we want here. So they are two somewhat different ideas. Cool. I will move on then. Okay, so here we want to show that if A and B are independent, they cannot be mutually exclusive. And then we want to show that if A and B are mutually exclusive, they cannot be independent. And then we want to suppose that A and B are mutually exclusive and want to show this result here. So let's begin with part one. So part one, we want A and B to be independent events, and then we want to somehow show that they can't be mutually exclusive. Remember that there is one condition on this, and that's that probability of A is strictly greater than 0, and then the probability of B is also strictly greater than 0. And we're going to use that fact to show our result here. So, in other words, if they were mutually exclusive, that means there are no elements in A and B together. So, in other words, A and B is going to be the null set, right? Because there are no common element in between them. And the probability of the empty set is equal to 0. So that is one of the facts that we have if we had mutually exclusive events. But we're given the fact that A and B are independent. So what that means is that we can break up this AND structure here to be the probability of A times the probability of B, because A and B don't depend on each other. But that's a problem, because we've shown that the probability of A and B is 0, which means that the product of probability of A times probability of B must be 0. So either probability of A is equal to 0 or probability of B is equal to 0. But that can't happen, right? Because the probability of A is, well, strictly greater than 0. And the probability of B is also strictly greater than 0. So when we have two things that are strictly greater than 0, and then we multiply them together, we can't possibly have 0. So this can't possibly happen. Which means that if A and B were independent, they can't be mutually exclusive. And that's how we can show that if A and B were independent, they can't be mutually exclusive. In the same way, you can prove the other way around as well. So if A and B were mutually exclusive, they can't be independent because of pretty much the same idea. So A and B are mutually exclusive implies that the probability of A and B is equal to 0. But then if A and B were independent, that means the product of probability of A and probability of B must be 0. But that can't happen because we said that the probability of A is greater than 0, probability of B is greater than 0. The product of two positive values can't be 0. And so if they are mutually exclusive, they cannot be independent. Cool. Does anyone have any questions regarding this proof? If not, then we can go on to the third question. So third question, we wanted to show this result here. In order to show this result, the first thing we want to do is to break up the conditional probability here into a fraction of two probabilities. So we're going to use the fact that the probability of A given B, so the little line here indicates that B has already occurred. And we want to calculate the probability that A has occurred given that B has already occurred. To do this, we want to calculate the probability that they happen together. And then we want to divide that by the probability that B has already occurred, because our sample size has actually decreased. So we're not considering extraneous information such as the probability of B not happening. Instead, we just want to focus on the probability that B has already occurred. So if we use this conditional probability, then we can break it up into, so this one, that one should be and here, and then this one should be or. There we go. So the probability that A given A or B is equal to the probability that both A and A or B has occurred, divided by the probability of A or B, just by simply substituting into this result here. In doing that, well, A and A or B, if we consider a Venn diagram, this is, let's just say event A, and then this is event B, I don't know. Then we say A and A or B. So A or B is this entire thing. Let me draw it in pink. So it's going to be this result here. So I'm going to draw like this. So this guy is going to be this entire thing here. There we go. So this is A or B. So it's either in A or B or both. And then the event A, I'm going to draw it in red, is this guy here. So I'm going to, including the intersection. And we can see that the only things that intersect between these two is this entire thing here. So we know that the probability of A and A or B is just the probability of A, because we can simplify A and A or B into the probability of A. And so the bottom in this case, because they're mutually exclusive, remember that the probability of A and B, well, that's equal to 0. So in general, you have that this is also minus the probability that A or B has occurred. No, A and B, sorry. A and B. But we know that this part here, that's equal to 0. So what we end up is just this result here. The probability of A or B is equal to probability of A plus the probability of B. And so if we substitute everything in, then remember that the top gets replaced with the probability of A, the bottom gets replaced with the probability of A plus the probability of B. And that's how we can show this result. Cool. Does anyone have any questions? Cool. If no, I think we have a few more. We have one more question. So you've also learned a little bit about joint density or joint density functions. So you can join two random variables together and you'll get a joint density function. You don't often get assessed with this because it's a little bit a little bit rigorous in trying to define what these are, but I thought that I would put one in just in case you do get asked a question on this. It's a very simple question asking us to find the marginal density. So we know that x and y are continuous random variables, and we have a joint density, which is this guy here. And we want to calculate the marginal density. So the marginal density is just given by f subscript y, or we can have f subscript x as well. So this is a function in terms of y. So in order to do this, we basically want to consider all of the x values. So we want to integrate over all of the x values of this joint density function. And remember that x and y are independent of each other. So x and y don't depend, which means that y is not a function of x. So you actually want to partially integrate it. And we know that x will go from 0 to 2. So that means your bounds go from 0 to 2, and you're considering the integral of 1 over 8 times x plus y. And if you just integrate that with respect to x, and then you substitute 0 and 2, then you get a quarter times y plus 1. Cool, not too hard. And you can also do the same thing with x. I'll leave that up to you. So instead of f of y, you have f of x, and you basically swap the x and y's around. So instead of integrating with respect to x, you're integrating with respect to y in this case. Cool. So that was the end of probability theory. So it's quite lengthy, but I think a lot of the concepts that you learn is pretty straightforward. So we'll go through one question regarding random sampling and CLT, and then we'll take a 10-minute break, and then we'll go on to the actual statistics. Cool. So this comes from the 2018 semester 2 paper. So we have a random sample x1 up to xn of size n from x. The probability pi can be estimated. So this is a follow-on question from the Bernoulli distribution that we had before. So I'm just going to highlight that distribution really quickly. So remember that our p of x, our mass function is given by, I think it was 1 minus pi. I'll just do this. Pi if x is equal to 1. X equals to 1. And 1 minus pi if x equals to 0. X equals to 0. And then we showed that the expectation, expectation of x, well, we showed that was equal to pi. Pi. And then we also showed that the variance of x was equal to pi times pi 1 minus pi. Pi times 1 minus pi. And there we go. Cool. Okay, so we're just going to use these facts here to then do some of the problems. So, some facts about the random samples. So first of all, each of the xi's are independent. So what that means is that each of these guys here are independent of each other. And the second thing is that each of these xi's are also identically distributed, so they share the same mean and they share the same variance as well. So using these two facts about random samples, we can then infer some things about, the distribution of the p hat and some other things. So we want to show that the standard error of p hat is equal to the square root of pi times 1 minus pi divided by n. So we also want to observe some additional facts, that because all of the xi's are independent, then when we take the variance of a sum, that's equal to the sum of the variances. Because remember that if xi's were independent, then the variance of x1 plus x2 is the same as the variance of x1 plus the variance of x2. And also the variance of a linear combination ax plus b is equal to a squared times the variance of x. So whatever is in front of the x, you basically square it, and then you get a squared times the variance of x. And so if we take both of those facts together, so if we plot both of these facts together, then we know that the variance of 1 divided by n times the sum is equal to, well, we can first of all take out the 1 over n, and we can take it out. Remember that we have to square it as well. So 1 over n squared times the variance of the sum. And then remember that the variance of the sum is equal to the sum of the variance. So we started off with the variance of this entire expression here, and then we ended up showing that that's equal to 1 divided by n squared times the sum of the variances. And the good thing about this is that all of these variances are the same, right? Because xi comes from a random sample. That means that they are identically distributed, meaning that they share the same variance. So all of these variances will be the same as well. All right, so putting everything together, we have the following. So we have that p hat was equal to this sort of average. We're basically taking the average of all of the random samples. And then we know that, well, that's equal to 1 divided by n squared times the sum of all the variances. But because they're identically distributed, but then we have n times the variance of whatever x is. And the variance of x, because it comes from the distribution of x, that's equal to pi times 1 minus pi divided by n. So the standard error is given by just approximating the standard deviation with the standard deviation of the random sample that we're given. So because this is the variance, the standard error, we just take the square root of the variance, and that's equal to the square root of pi times 1 minus pi divided by n as required. So to recap, the main thing that you need to know about random samples are these two facts. The fact that they are, first of all, independent from every other event. And then they are also identically distributed. And then using these two facts, we can infer this result here. And from here, we can kind of just play around with it and then see what we can sort of come up with. So that basically concludes the first half of the workshop. We'll take a 10-minute break, and we will finish off with confidence intervals, hypothesis testing, and Anova testing. So I'll see you guys in a bit. So we got a question. So what's the significance of the p-hat notation when we're finding probability pi? So remember that this p-hat is not a accurate, or it's not really an accurate distribution. We're actually just approximating we're approximating the distribution itself, right? So the probability pi can be estimated using this estimation. And you would have learned about estimators in your course. Basically, you basically just want to take a sample from X that, but basically you don't want to have any information about what these X's are other than the fact that they come from this original larger set X. And then the probability pi can be estimated using the estimation that we have here, p hat. So this is just basically saying I want to estimate X, and then the probability pi basically comes from the probability of the estimator. And because the estimator is not exactly the same as X, we are naturally going to have an error. And that's where we have the standard error as well. So the significance of p hat is that in general, when you go out into the real world, you won't have exact data, and you also won't have larger and large samples of data that accurately gives you the exact value of X. In fact, you need to take a smaller sample of that distribution in order to kind of do some particular things with it. Because if you take, say, 10,000 samples, that can be quite difficult to manage. So you want to take a smaller sample, and that's where the estimation comes from. And in doing that, you also naturally will have error, but the probability itself will still be the same because you're taking the same sets of data. So you're going to have the same distribution all the way through. Oh, that's a good question as well. I'll try to erase this. Oh, we can. Okay. If you guys have any other questions, feel free to pop it in the chat. I do read them as well, and I'll try to answer as many questions as I can. I hope your studying has been going well, especially because exams are so soon. There we go. We got another question regarding study tips. So, do you recommend short notes for the exam? I think what's more important are notes that cover the entire scope of the course. So, you should try to have at least concise notes that at least touches on a little bit of every single topic. Otherwise, you risk missing some important tricks, results, and etc. Yeah. Will you be covering more MATLAB-oriented solutions to questions? That wasn't in my agenda, especially because I don't often use MATLAB as well. But when I release all the documents, I can also release a supplementary content regarding some things to do with MATLAB. So I can probably write up some MATLAB sort of cheat sheet, I guess, for you guys to use as well. But that wasn't on the agenda for today's seminar or workshop. So I'll probably just remind myself to write up another, to kind of write up a document for that. So MATLAB supplementary document. Cool. I think the most important things you need regarding MATLAB is really just calculating things like t-distributions, f-tests, and probably a few other distributions as well. So yes, I will remind myself, I'll probably do that tonight. So when we do release the slides, I'll also release those documents as well. Cool. All right. Erase. Oops. How are you guys feeling for the final exam? Hopefully it should be okay. In any case, we'll get started again. So sort of the last 30 minutes to an hour, depending on how we go with time, we will be covering 3 relatively big topics. So we'll go through some confidence interval problems, and then we'll go through some hypothesis testing problems, and then we'll finish off with, I think, 3 Anova Test problems. So let's get started. So confidence interval. So I guess we'll get started with the problems. So let's have a look at the problem here. So wildlife biologists inspect 153 deers taken by hunters and find 32 of them carrying ticks that test positive for Lyme disease. We want to create a two-sided 96% confidence interval for the percentage of deer that may carry such ticks. So we want to, first of all, we want to kind of break it down a little bit into bite-sized pieces. So the first thing that draws my attention is, I'll highlight this, the fact that we are creating a two-sided 96% confidence interval. So if we think about the distribution, what this means is the following. Say that we have, so most likely we're going to either use a t-distribution or a normal distribution, depending on some other information that we will go through in a bit. So because it's a two-sided 96% confidence interval, what that means is that we're considering what happens around the mean, and then we are considering what happens around the edge case or the endpoints. So 96% confidence interval really means that the middle part here, so I will draw this in orange, I guess. The bulk of this portion here all of this portion here, that will be 96%. So what that leaves is that these two areas here, so I'll highlight them in gold. So both of these will be 4% together. So because we are thinking about a symmetric, we're considering symmetric, considering a symmetry in the distribution, that means these two will share 2%. And so what we want to do is we want to find what this guy here is. This is what we call the critical point, or the critical value. We basically want to find what these two values are. And so how can we do that? Well, the first thing we want to do is to figure out whether we want to use a normal distribution or a t-distribution. And to do this, we want to think about how many samples we have. We have 153 samples because we inspect 153 people, or 153 deers. So the sample is above 30, so generally we should be using a normal distribution for this. But in order to actually check, we need to consider what happens to, I think, n times the probability times 1 minus p. And if in general that's greater than 5, I believe, then we use the normal distribution. And so p here is, well, we want to create a two-sided 96% confidence interval for the percentage of deer that may carry ticks. So that means that p here, well, that will be 32 divided by 153. Oops, 153. And you can check for yourself that this should be, above 5. And in general, this is because of the fact that we have greater than 30 samples. So that's a test that you can use to determine whether to use a normal distribution or a t-distribution. Cool. So once we know the distribution, then the next thing we want to do is to consider or to find the significance level. And I kind of showed it to you graphically, what we did to find the significance level. So it's a two-sided test, which means that 4% will be shared on both extreme sides of the distribution. And so the significance level is going to be, 1 minus 0.96 divided by 2, which becomes 0.02. So 2% is your significance level. And so we want to consider the z-score of 1 minus alpha, which is 1 minus 0.02, which is 0.98. So we consider the z-score of 0.98. To do that, we want to calculate the norm inv. So the norm inv will calculate, highlight this in, okay, I guess it didn't. There we go. So the norm inv will calculate the probability, or actually no, yeah, so the probability that, okay, this is not x, this should be z. Z is less than a, and that's equal to 0.98. 0.98. Cool. And then norm inv will basically calculate this guy here. And so once we get this value here, then we kind of just put it aside a little bit, and then we want to do another calculation. So the third step, once you find the z-score, next thing you want to find is the standard error. So remember that the standard error is given by sigma divided by the square root of n, and that's equal to pi hat times 1 minus pi hat. Pi hat is given by 32 divided by 153. You can calculate this by simply going 32 divided by 153, simply because we want to find the percentage of deer that carry the ticks. So that becomes 32 divided by 153. Is there a difference between lowercase z and uppercase z? There is. So the lowercase z is, well, in our case, it's going to be the z-score, right? So in general, lowercase z means, well, okay, uppercase z means an event. So if we have an uppercase z, that means an event. And then the lowercase z just means some number. So you're basically considering little case z of 0.98, meaning the number given when you plug in into this formula here. Yep. So uppercase z is event, lowercase z is just a number. So it's similar to how we did this before. P of x, so capital X equals to little x. There. So the capital X is just an event. The little case x is just the number. Cool. So going back to this, well, we calculate pi hat, because remember that we are technically estimating something. So that's equal to 32 divided by 153. And our sample is going to be 153. So once we have that, we can calculate the standard error, and that's equal to this. So we just simply substitute these numbers into our standard error formula. And then we now have a z-score, we now have the standard error, we can begin to construct the confidence interval. So the confidence interval is given by pi hat, because that is the average of the average proportion of deers that test positive for carrying ticks. So we take the mean minus the z-score times the standard error, and then the upper number for our confidence interval is the same thing. So it's going to be the mean proportion plus the z-score times the standard error. And once we do that, we get this confidence interval here. Cool. So we have another example here. So in August this year, Roy Morgan Research published a poll on rugby viewership of New Zealanders, the poll of 6,422. So already you should immediately think this is the number of samples that we have. Randomly selected New Zealanders found that 43.6% of them watch rugby on the television. We want to find a 95% confidence interval for the true proportion of New Zealanders who watch rugby. So for true proportion, it's essentially the same idea. You want to find the significance level. So we know that because it's a true proportion, it's going to be a two-sided interval, a confidence interval. And we know that we have 6,422 randomly selected New Zealanders. And so what we can know is that this is going to be a normal distribution. And so we find the significance level, proportion, we're taking a two-sided interval. And so we know that 5% is shared on both extreme ends of the distribution. So again, this gives us alpha equals to 1 minus 0.95 divided by 2, which is 0.025. And so we're finding the z-score of 0.975. On MATLAB, that you can calculate as norm in of 0.975. And that's approximately 1.96. Cool. So the next step, as always, is to find the standard error. So to find the standard error, we use sigma divided by the square root of n, and that's equal to the square root of p times 1 minus p divided by n. Our sample size is 6,422, and we know that the proportion of people watching rugby is 0.436. So we can just substitute everything in, and then we get the standard error to be approximately 0.00618, etc. Cool. Does anyone have any questions regarding this? So simply our confidence interval is 0.436 plus or minus z of 0.975 times standard error. And that will give us this. Cool. So to recap, to find the confidence interval, you first of all need to determine whether or not it's a normal distribution or it's a t-distribution. Then you need to find the z-score. So what you need to find is the significance level, and to find the significance level you need to find whether it's a one-sided or a two-sided test. And then you find the standard error, and then you just substitute it into the formula here. Cool. So we're moving on to hypothesis testing. So this is going to be one of the more important topics when it comes to your exam, because a lot of questions kind of rely on hypothesis testing. Can we think of z as how many standard errors away from the mean? Yes. So the z-score itself is just basically how many standard errors away from the mean you actually are. You can think of it like that. Basically, the idea is that when you have, that's a terrible normal distribution. Let me try again. That's good enough. Basically, the z-score is how many standard errors you are away from the actual mean here. Well, it's definitely not symmetric, but so if you are here, or if you basically cover this entire thing, you're about 66%, which is about two standard errors away. And if you're here, you are 3 standard errors. And then you basically find the critical value here, which is your z-score. Cool. Yeah. So on to hypothesis testing. So hypothesis testing is probably one of the more important topics, simply because it's how we can infer new conclusions, and we can kind of reject old conclusions if we wanted to. So Ooh, that's a very lengthy question, but let's kind of dissect these problems. And you'll notice that in a lot of these hypothesis testing problems, you'll have a fat text that you need to read. But once you dissect it a little bit, then it should be a little bit easier to understand. So the final step in the manufacture of graphite electrodes is graphitizing in an electric furnace, blah, 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 blah. So this is just all context. The more important thing is that 15 specimens were tested. So that is your N here, your sample. So that's N. Assume the predictor X is time and the response variable Y is resistance. The linear regression model is given by this, and we are asked to perform a hypothesis test to determine whether the variable X is significant in this model at the 5% level of significance. So we want to perform a hypothesis test to determine whether the variable X is significant. So here, most naturally, what we want to think about is how we might want to use beta 1. So beta 1 is going to be the variable that we want to think about, because that is going to be the one that will affect how X is significant, or how X affects what Y is. And finally, we are given that it's a 5% level of significance. So from there, then we can begin to write out our hypothesis test. So in any hypothesis test, the first thing you want to do is to write out your hypotheses. So there are two hypotheses that you need to write out: the null hypothesis and the alternative hypothesis. The null hypothesis is the one that you want to reject. So you want to find evidence against it, and then in favor of the alternative hypothesis. So our null hypothesis is that X is not very significant to Y, meaning that even if we get rid of what X is, that won't really change what Y is. So our null hypothesis, H0, is going to be beta 1 equals to 0. And that means our alternative hypothesis is going to be beta 1 is not equal to 0. Yep. Cool. So the second step is to determine the test statistic. So we're only given 15 specimens. So what that means is that we can't really use the central limit theorem to infer that it will be normal distributed. So we need to use a different strategy. And we're going to be using what we call the t-test, or the student t-distribution test. So to use the t-test, we need one piece of information, and that's what we call the degree of freedom. I will highlight this in blue. So we need the degree of freedom. And we know that beta 1 and beta 0 have to be known. And so the degree of freedom is going to be n minus 2. Because we need beta 1 and beta 0 to be defined beforehand in order to actually test all of the hypotheses. So that means we have n minus 2 degrees of freedom, where n is going to be clearly the number of samples. So in this case, the degree of freedom is going to be 13. So our t statistic is going to be t of 13, 0.975. And you know that it's 0.975 because it's a two-sided test. And the way you know it's a two-sided test is because our hypotheses are beta 1 is equal to 0 and beta 1 is not equal to 0. And that really means that we're considering the extremities, or we're considering the endpoints as well, or both endpoints. Whereas if you had something like beta 1 was greater than 0, then we're only considering one portion of our distribution. But because we're only considering beta 1 is not equal to 0, we consider both endpoints. Cool. So that's why we divide our alpha by 2. And so that gives us 1 minus 0.025, which is 0.975. And so our t statistic is going to be t of 13, 0.975, which is 2.160. And what that means, if we think about this graphically, I'll do this in magenta. Oh, okay. What that means is that if we consider our t-test, our t-distribution, oh my gosh, okay. Very similar to the normal distribution, or the normal distribution. It's going to be symmetric. Oh, okay, that's definitely not symmetric. I'll do this again. Okay, whatever. Just assume that it's symmetric. And then so we're considering at the 97.5%, this portion here is 2.160, 16, and then this portion here is minus 2.160. Cool. And then we basically want to find evidence that our observed value is going to lie between these portions here. And if it is, then we have to reject it. If it doesn't, then we don't reject it. Cool. So the next thing we want to do is to determine the rejection region. So the most general rejection region is going to be given by this formula here. So we're given the t statistic, and then we multiply by the standard, or the sample standard deviation, divided, so the standard sample mean divided by the square root of the standard, the sample variance, which is the sample standard deviation. And so if beta 1 is not in this region here, then we reject the null hypothesis. That's equivalent of saying that beta 1 would lie somewhere in between these two portions here. But we can do even better, because we can use the observed t statistic to see that, well, t observed is just the estimate divided by the standard error. So this is just basically what this is saying. So the estimate, well, we're given the MATLAB output here. So we're given the MATLAB output here to be, well, the t statistic error of the estimate is going to be minus 0.16506. And the standard error is given by 0.011475. So when we just plug that into our observed, then we get minus 14.384. Right? So that's going to be the observed value of our t statistic. Then what we want to do is we want to reject it if our t observed is greater than this number here, or if t observed is less than the minus of this number here. And so this is the same as saying our observed value lies in this region here or this region here. And clearly it does, so we have to reject the null hypothesis. So the last step, so once you find the rejection region, the last step you want to do is to write out your conclusion. So we reject H0 because there is strong evidence that there is a correlation between time and resistance. And that's it. So the hypothesis testing really requires 4 steps. The first step is to write out your hypotheses, then determine what statistic you want to use. And the third thing you want to do is to find the significance level, and you also want to find the rejection region. And then the last step is to write out the conclusion. And whatever conclusion is either we reject H0 or we don't reject H0. We don't say we accept H0. We say we either reject it or we don't reject it in favor of the alternative hypothesis. Cool. All right, so let's do another example. This time we want to show the rejection region. So in August this year, so we are going back to the Roy Morgan research problem. They published a poll on rugby viewership of New Zealanders, etc. And we want to assume Rugby New Zealand want to be able to demonstrate that rugby viewership is in excess of 40% of New Zealanders using a sample size n. What are the appropriate null and alternative hypotheses? So again, you look at the question, you want to find evidence in favor of excess of 40%. So that means you assume that the current accepted hypothesis is that the rugby viewership is 40%, and then you want to find evidence that it is greater than 40%. So our null hypothesis is that the mean viewership is about 0.4, and then you want to find evidence for excess of 0.4. So here we can see that instead of saying it's not equal to, we have a greater than sign. What this means is that we have a one-sided test. So I will just write it out. We have a one-sided test. Sided test. Ooh. Cool. So the distribution is approximately normal because, we have enough samples. So we assume that it is approximately normal because we have 6,422 samples. And of them, we want to shrink it down to n, a sample size of n. So it's approximately normal with mean mu equals to 0.4. And then the standard deviation is, it's going to be the square root of p times 1 minus p divided by, that should be n, not square root of n. So we have 0.24 divided by n here. Cool. All right. So the next thing, we want to find the rejection region. So we can standardize it so that it is asymptotically normal, also asymptotically standard normal. This gives us a z equals to x minus mu divided by sigma. That's just the normal, so that's just the standard distribution conversion to a standard normal distribution. And then we plug everything in. So we note that the significance level is 0.05. So we don't divide it by 2 because of the fact that it's a one-sided test. So we consider the z-score of 0.95 instead of 0.975. So we have to be careful that it's a one-sided test and not a two-sided test. Cool. So the rejection region occurs when we fall in this range here. So if we think about this. Oh my god, okay, I don't want that. It's gonna be like that. So if we consider when z is in this region here, so remember that this is your critical value. So this is this guy here, so this guy here. So that's going to be at this point here. So we consider the rejection region is all of the cases where z falls outside of this range. And so because z is equal to this portion here, we can just solve for x. So we can just rearrange for x, and then we get that x is approximately greater than 0.4 plus 0.806 divided by the square root of n. And so that gives you the rejection region, so the region in which you reject the null hypothesis. Does it make sense? So the rejection region is basically all of the values in the outer area here. Cool. Finally, the last hypothesis test before we go on to Anova tests. So we'll quickly blitz through this. So write the null and alternative hypothesis. So here we have the linear regression again. So we use the t statistic. We want to find the t-test with degree freedom n-2. So in this case, we have the test statistic t28. So we're given that n equals to 30 here. So we basically want to look at this, and we're going to instead look at the p-value. So this will be a p-value problem. So the t observed is given by this portion here, minus 7.8, because it's the t statistic at PPV, of PPV. So we want to find the portion in which, so for the p-value case, the p-value is given by 2 times the probability where the t statistic here is greater than whatever this value here, the absolute value of this. So this is the same thing as saying you are in this region here. In this portion here. And so this is the same thing as saying the p-value is 2 times the probability that t is greater than 7.8. And notice that t follows a t distribution with degree of freedom 28. And that will give us the p-value of 0. So we can see that the p-value here is given as 0, which means that there is strong evidence, because we know that if p is less than, I think, about 0.01, then we have to reject it. And because our p-value is 0, then there is strong evidence against the null hypothesis, and so we reject H0. Cool. All right. That basically concludes hypothesis testing, and the last chapter we'll go over is analysis of variance. So Anova is basically another hypothesis test, but this time we're basically going to be using the Fisher F test instead of the standard normal distribution and the t statistic. All right. So we're given a set of data again, and we're given 3 different types of periods. So we have the early period, evening period, late night period, and we're given 24 different data points. The question asks us to construct the Anova table. So the treatment here, so the first thing we want to find is the degree of freedom of the treatment. And the degree of freedom of the treatment is given by how many times can you compare these three treatments. So we can compare early with evening, we can compare early with late night, and we can compare evening with late night. So there are 3 different ways of finding or of comparing these 3 treatments. So the degree of freedom is going to be, 3 minus 1, which is given by 2. So the first thing you want to do is to find the number of treatments, which is to find the number of ways in which you can compare these treatments here. And then what you want to do is you want to fix one of them. So you have 1 less degree of freedom, and then that becomes your degree of freedom of the treatments. So you have 2 degrees of freedom for your treatment. The second one is basically you want to calculate the total degree of freedom, and that's going to be n minus 1, where n is the number of cases. So in this case, we have 24 different cases. So the total number of degrees of freedom of the total degree of freedom is going to be 23. And you can also think about the degree of freedom of the total is just the treatment degree of freedom plus the degree of freedom of the error as well. So, and adding these 2 up will give you the degree of freedom of the total. Cool. For number 3, we want to find the sum of squares of the error. So to do that, we just multiply the mean square with the degree of freedom, and that will give us 53,529. So that tells us the sum of squares. Cool. So that's 1, 2, and 3 done. Number 4 can be calculated in a very similar way. We're given the degree of freedom. We calculated the degree of freedom, and we are given the sum of squares. So what we want to do is we want to divide the sum of squares by the degree of freedom, and that will give us the mean square. And to do that, we just basically take this number here, divided by 2, and that'll give us 52,817.5, which is approximately 52,818. And finally, the observed value of the F statistic is given by the mean square of the treatment divided by the mean square of the error. So that's something that you kind of just have to remember. So the observed value of the F test is given by the mean square treatment divided by mean square error, which is 52,818 divided by 2,549, which is approximately 20.72. Cool. So once we fill out the Anova table, we can carry out the Anova F test. So we are given the significance level to be alpha equals to 0.05. And so let's just carry out the hypothesis test. So the first thing you want to do is to write out the null and alternative hypothesis. So here we want to determine whether there is a difference in average downloading time among these 3 periods. So we want to find evidence against the fact that they are all the same. So our null hypothesis is that they have the same time. So the alternative hypothesis is saying that they are not all the same. And just be careful in saying that not all the same is not the same as saying mu1 is not equal to mu2 is not equal to mu3. Mu1 not equal to mu2 not equal to mu3 means that they are all distinct. Whereas 2 of them can be the same, but all 3 of them can't be the same. Cool. So once you do that, you identify the test statistic, and because we're doing an Anova test, the most appropriate test statistic to use is called the F test, or the Fisher F test. And it will take 2 parameters. So the first parameter is k minus 1, which we already calculated in the table, and n minus k, degrees of freedom. K is the number of treatments, and n is the total number of cases. So here, k minus 1, that refers to the degree of freedom of the treatment, and n minus k refers to the degree of freedom of the error. And in doing that, we have 221. So k minus 1, because k is 3, k minus 1 gives you 2. And then n minus k gives you, well, n in this case is 24. So n in this case is 24. And then k is given by 3. So that means we have n minus k, which is 21. So we consider these test statistic F221. The third thing you want to consider is to calculate the observed value of the test statistic, but we did that already using the Anova table, and that's clearly given by number 5 here. Also, I'll highlight this in red, maybe not in red, okay. In any case, number 5 is the test statistic, or is the observed value of the test statistic. So we calculated that to be 20.72. And the last thing you want to do is to determine the rejection region. So the rejection region is when the observed value is greater than this value here. And it's 0.95 because the significance level is 0.05, and the Fisher F-test is a one-sided test. So the Fisher test, or the Fisher F-test, remember that it's something like this. Oops. And then we'll basically, we basically want to calculate the tail component here. Cool. And so we have, if we consider F inverse of 0.95 to 21, so 221 is the degrees of freedom. That gives us 3.467, but clearly 20 is greater than 3, so we reject it. And then the last step is to just write out the conclusion. Cool. So we have another example here. Basically, it's the same idea. We want to construct this Anova table using all of the information that we have. So k minus 1, so the number of treatments is 3 because, well, we can compare FWD with AWD, FWD with RWD, and AWD with RWD. That gives us 3 different treatments. So that means the degree of freedom of the treatment is 3 minus 1, which is 2. And then for number 2, it's n minus 1, where n is the total number of cases. So the total number of cases in this case is just the sum of n1, n2, and n3. So that's 215 plus 78 plus 94 minus 1, which is 386. And you can check that when you add this with this, you end up with the total. The third one, because we don't really have any data sets to go off of, we can use the fact that the sum of squares of the total is equal to the sum of squares of the treatment plus the sum of squares of the error. And so we can take this portion here minus this portion here, and then we get number 3. Cool. Number 4, again, it's the same idea. The mean square can be computed by taking the sum of squares and dividing it by the degree of freedom. And then the F statistic can be computed by the mean squared of the treatment divided by the mean squared error, which gives us about 59.07. And so we can carry out the Anova test again. So the first step is to write the hypotheses. So in this case, we want to determine whether there is a difference in highway fuel efficiency. So we want to find evidence against the fact that they're all the same. So our null hypothesis is assuming all of these are the same. And then the alternative hypothesis is that they're not all the same. Step 2, we apply the Anova Test using the Fisher F test statistic with k-1 and n-k degrees of freedom. And so that gives us F2 384. We calculate the observed value, that's given by 59.07. And the second last step is to just find the rejection region. So we reject the null hypothesis if our observed value is greater than this value that we find here. And we can find this value here by taking F inverse of 0.95 given to and 384, which is 3.0192. And then the fifth step, the last step, is to write our conclusion. So we reject H0 since there is very strong evidence that fuel efficiency among drivetrains are not all the same. And that's how you can conduct an Anova test, and more specifically a hypothesis test as well. That basically concludes the end of the statistics workshop. So tomorrow at the same time, we will have the numerical methods one. So it will be a different link as well. So check your email tomorrow for that link. Otherwise, best of luck with your exams, and hopefully today has been